matrix form, it has the following structure. You get y I prime squared plus zi prime squared, and then here we get xi prime squared plus zi prime squared, and here we get xi prime squared plus yi prime squared. Then we get these off-diagonal terms, minus x times I minus x times z, and of course here minus y xi, and here minus y zi, and of course you can already guess zi xi zi yi. Now remember that we have to take for the whole torque, we have to take the integral over the volume times this mass I, and remember everything is then multiplied with this omega dot, right? So this guy is then multiplied with omega dot x, omega dot y, omega dot c, which is, I would say, are the angular accelerations, right? Or you could say in a vector form, it's omega dot. Then what is this guy? Well, that is exactly the mass moment of inertia thing. I see suddenly that my live stream is down. What is going on here? Let me check that first. What is going on, guys? That's a bad connection, or what is this? Yeah, I'm live again. Okay, sorry for that. Everybody's working online, and maybe that's the bandwidth is a bit low. Okay, yeah. So then, if I then evaluate this integral thing, then that's exactly the mass moments of inertia term. So this is then exactly y capital number. And we recognize stuff. For instance, we call this y zz, and that's then this term. That is the integral of xy prime squared plus yi prime squared, yeah, times dmi. And remember, that's exactly the mass moment of inertia we have about the z-axis, the third axis, which we had in our 2D, in our 2D Euler equation. So that are a single term. But for the rest, and then we have all these off-diagonal terms with a minus sign. For instance, y xi is then minus the integral of xi yi primed dmi. And of course, when the body is symmetric, then these terms go away. So in a symmetric case, so if there's a symmetry with respect to yi, then this term will go to 0. So if you have two symmetries in a body, then all these diagonal terms will all go away. But you can get those terms also away. So in general, the mass moment of inertia matrix has this form: yxx, yxi, and yxz. And then here we write yx, but notice that of course the thing is symmetric. So if I write zx, that's identical to xc. So the zx term here, this term is identical to this term is identical to this, because there's no order, of course, in this integral. And then yzi, zz. Now this is a 3×3 matrix, and of course it's symmetric. That's important to see. But most of all, you can also transform everything, to a diagonal matrix, and you can do that with the eigenvalues and the eigenvectors. With the eigenvectors and the eigenvalues, and what are then the eigenvalues? Are exactly the diagonal values of this matrix. So, and we call that the principal axis. these eigenvectors, the principal directions actually, sorry, principal directions. And in the principal directions, and let's put a bar over this, then we get a matrix of this form. We get a bar IXX, and we get only principal values here, and that's easy, and we get all zeros here. Now it's sort of super easy to find out what are principal x's, because most bodies have some symmetry, so like if I look at this body, I immediately see what the principal x's are. This one is a long one, this one there's some symmetry about this one, so initially we see, oh yeah, these three along this direction, and perpendicular to this one, those are the principal axes. So that's easy. In the case of an apple, Newtonian apple, well, you already know there's a symmetry about this axis. So if the apple is really nice and round, even that two of the principal values in this plane should also be the same. So in the end, then this matrix will only have one value, and these two are then identical. So with reasoning you can already find a lot of things about it. Okay, now let's move on to an example. Well, we didn't discuss one part, and that is this second part, and that's this part, and that is rather complex. In the end, you will see it also has, of course, contributions with the quadratic part of this xi prime, meaning that in the end you will also have terms like this in that, but it's also quadratic in the angular speed. Now if you go, it's a rather lengthy derivation, but if you go into the derivation, then finally the final result will be like this. You get then the sum of the torques is this invariant thing, mass moment of inertia, and this was we call it the convective acceleration, and the source of that guy is of course is this term here. Okay, then if you write down this equation in terms of, and you use principal axes, you see there are a lot of zeros, so there are a lot of terms which will go away. Then this Euler equation will have a somewhat simpler form. So then let me write down for a body with principal axes, principal axes x, y, z. One part is super simple, some x is m x double dot, some forces in the y is m y double dot, some of the forces in the z is m z double dot. And maybe I should say that's at point C, where C is the center of mass. And we use principal axis. Okay, now the Euler part, then we get the sum of the torques, and now I'm writing equation for equation, because everything is decoupled because of all these zeros which are gone. So we get Ixx times omega dot in the x direction, super simple, but now we have this extra term, and the extra term comes from omega cross I omega. Yeah. And how does that work out here? Well, I get y I minus I z times, of course, omega y omega z. In the y, oops, that's not a nice m. In the y direction, I get mass moment of inertia in the y direction times the angular acceleration in the y direction plus, well, you can add it by cyclic permutation, right? My cyclic was not so good. Of course, cyclic, you come zz minus, and I've got the y, so it has to be an x. Then it's omega z omega x. And then the last one talks about the z-axis, is y zz omega dot c. We already know that from the two-dimensional case, but now we have to add xx minus yy times omega x omega y. And that's sort of interesting. This part we already know. That was the 2D case. And then the large part, of course, is the 3D case. So as I said at the beginning of this lecture, moving out from a two-dimensional world to a three-dimensional world, you would say, oh, that's only one step, one dimension more. But if we look at the rotational equation, then it suddenly increased enormous in complexity. From this one simple equation, we went to 3 highly coupled equations with nonlinearities. And that has some consequences. That has consequences also on the dynamic behavior of rigid bodies in space versus rigid bodies in a plane. And we will see, and as an example, I will look at such a strange, unexpected behavior. The example is stable rotation of a torque-free 3D rigid body. And what are we looking at? Well, as an example, I want to look at this kind of thing. Everybody sees, of course, that this is a satellite in deep space, right? These are the solar panels. This is a satellite in deep space. And why do I say deep space? Because then gravity is 0, right? So let's presume it's rotated about this axis with some omega. And then there are no torques, right? Because it's in deep space, no gravity. There's also no solar wind or no drag or whatsoever. So the sum of the torques is really 0. So that's the what I say about the torque free. There are no torques. And then the question is this stable? In the sense, if there is a very small perturbation, so if we have omega is some omega 0 plus some epsilon, some small change in the angular velocity, will then the epsilon go to 0 or yes or no? Will the epsilon in time go? So that's what we want to investigate. Now let's assume in this case that it's a nice symmetric body, and there's even more symmetry in a satellite than I assume now, but let's assume we have just what I say the principal axis. So we have a diagonal matrix with the mass moments of inertia A, B and C. And for now I assume they're distinct. Then I start with an initial angular velocity of omega 0 and 0. So we rotate about, come back to me. We rotate about this axis, and then the question is, does it stay in rotation about this axis or does it wobble or flop around? So this is the initial speed about this axis. So that's this mass moment of inertia, right? So the IC, if you write it out as this nice A, B, C, and the rest is all zeros. Okay, how do we investigate our question about stability? Well, of course we use our Euler equation of motion, right? Euler equation of motion. And what does it say? Well, it says that the sum of the torques is mass moment of inertia times angular acceleration plus omega cross I omega. That's our Euler equation. And what do we want to investigate? We want to investigate small changes of the angular speed. So then we have to presume that the angular speed which we are using here, that we have to write that angular speed as the initial angular speed plus some small change, delta omega. And likewise with the torques we will write, well yeah, the torques are of course, in general the sum of the torques are the initial torque plus a small change in the torque. Well, of course, and for now, of course, we assume that this is 0, right? And we have torque free, so we also assume there's no small change in the torque. So in the end, we want to have that's always 0. Now, what do? We just substitute this into our Euler equation. And of course, here we have a dot, so we also have to do omega dot is, well, this is then 0, and this is then the delta omega dot, because we assume some constant initial angular velocity, and then if we differentiate it, we get 0. Likewise, that there is no torque. Putting that into equation is just some scribbling, but of course we get m0 plus delta m, but we will see how that's 0. Then the first is the angular acceleration, omega dot 0, but that was 0, so let me already put that in, right? So there was a 0, plus r delta omega dot, and then plus, and now it's becoming complex, we have omega 0 cross omega, cross product with I times omega 0 plus delta omega. And that last part seems rather complex, right? Now this is 0, we assume. So here we remain I times delta omega dot. And now that second part, well, it's not so hard. You just have to do it piece by piece. By the way, this is not a cross, this is a plus. Sorry for that. So this is a plus delta, and this also breaks down in 2 parts. So let's do that. We get omega 0 cross product with, and then we get 2 terms, I omega 0 plus I delta omega. That's the first part. And then the second part is, of course, this delta omega. So we get delta omega cross product with, again, this stays the same, plus I delta omega. Okay, 0 I delta omega dot. So what does remain? We get plus omega 0 cross I omega 0, plus we get omega 0 cross product with I delta omega, cross I delta omega. Now already we can throw away a number of things. This is 0 because we only look at order, this is order delta omega squared, so we neglect that. We do a first order approximation. We do a linearized stability analysis. Now here we see all, here we see all, where are you? Here we see all delta, so there's a delta here, there's a delta, omega here, delta. Here we still have omega cross I omega. What is that? Well, remember that the basic equation was m0 is I times omega dot 0 plus omega cross I omega. Well, this was, we assumed no torque, we have no, we have a constant initial angular thing, so by definition this guy is 0, so we can cross that also out as 0. And the remaining equation is, of course, 0 equals I delta omega dot plus, and then we have these 2 terms, we have omega 0 cross I delta omega, plus we have delta omega cross I omega 0. And that's all up until the first order of a delta omega. So this is our equation. Now we're going to rewrite that, of course. First of all, we're going to look at the first part, this I delta omega. How does that look? Well, in our case, that's rather simple, because this diagonal matrix A, B, and C. And then we have, for the delta omegas, yeah, I presume to use for delta omega, I said, why don't we use alpha, beta, gamma dot? And it writes a little bit easier than omega x, omega y, omega z. So here we have alpha dot, beta dot, gamma dot. So alpha, beta, gamma are the small angular alpha dot, beta dot, gamma dot are the small angular speeds added to the initial one. And the question is, of course, do they grow or not? If we do this multiplication, we get this nice vector A alpha dot, B beta dot, and C gamma dot. So that's easy. Now the other part is, of course, a bit more complex. So we have to look at this first cross product and the second cross product. So let's look first at omega 0 cross I delta omega. Then omega 0 was this omega 0, 0, the initial speed. And then a cross product with, well, I delta omega is, of course, likewise, it's just a vector with these alpha dot, beta dot, gamma dot. Should be yeah. So that should be a A times alpha dot, B times beta dot, C times gamma dot. And then we have to do the cross product. That is not so. It's this times this minus this times this. And for the rest, it is cyclic. And that's, of course, 0 then in this case. Then the second part is 0. So that's 0 minus omega times C times gamma dot. Yeah. And then the last part is, so the last one is omega times B times beta dot minus 0, yeah. Then we have to do the other one, delta omega cross product I omega 0. So that is the delta omega was alpha dot, beta dot, gamma dot, and then cross product. So now it's a bit the other way around than above, but still. So the first is again 0, then the second one is, of course, gamma dot alpha omega, and the last one is minus beta dot A times omega. Okay, then we have to add up these two terms and plus these terms and make a nice equation out of that. So if we do that, we reorder all the terms, put that together, then what do we get? Well, we get A, B, C times alpha double dot, beta double dot, gamma double dot, plus, and then we have the other terms, the first one being above 0 minus omega C gamma dot, and then plus omega B beta dot, and then the other term is 0 gamma dot A omega minus beta dot A omega, and that all should be 0. Now I'm gonna reorder a little bit because it's interesting that everything is, of course, linear in this alpha dot and a beta. Oh, there is even not an alpha dot, right? It's only gamma dot and beta dot. So I can write this again, these two vectors, as a matrix multiplication in terms of alpha dot, beta dot, and gamma dot. So I rewrite that A, B, C, alpha double dot, beta double dot, gamma double dot, plus, and then I get a matrix, and I get alpha dot, beta dot, gamma dot equals 0. Now the first part, that's clear, that's all zeros, right? And moreover, there is no alpha dot in the equation, so this also goes away. And then we get, on the diagonal, we have nothing. So for the beta equation, it's all with gamma dot, and for the gamma equation it's all with beta dot. And so here's a 0 and here's a 0. And what is then on the off diagonal? That's A minus A minus capital C times omega, and on the other part you get B minus A times omega. And that should be 0. Right? Now some of you may recognize in this a sort of an eigenvalue problem. So we have a time derivative of we have something, and we have a time derivative of something, and we have two matrices, And then, well, you can assume that your delta omega, not the dot, sorry, your delta omega vector, which is alpha dot beta dot gamma dot, yeah, that let's assume that that has some exponential form, so it's some amplitude times e to the power lambda t. And then if we then add delta omega dot, which is this guy, then that is, well, some amplitude times lambda times e to the lambda t. So everything remains the same. So finally I then get, if I substitute that, I get the following problem. I get finally a set of equations which go like this: a times lambda, right, and then 0, 0, and then here's also a 0, and then b times lambda, and then here we get a minus, oh, I'm not so good at my minuses, minus c times a1, a2, a3 should be 0, and that should hold for all a's, and not that the a's are all 0, because that is sort of cheating. Well, if you want to have it for arbitrary a's to be 0, then there's only one way. Then this should be a non-regular matrix, or in other words, the determinant of this matrix should be 0. So the determinant of this matrix should be 0, and that leads you to the characteristic equation. And the characteristic equation is then, well, you have to take the determinant of this guy, so that's this guy times this determinant, and this is all 0, so you can skip that, because it would be this times this times this. The determinant, in this case, oh, capital D, is a lambda times, and then b lambda c lambda minus a minus, again, a minus c omega times b minus a omega. And that should be 0. And from that we want to solve the lambdas. Well, we can rewrite it a little bit nicer, maybe. Well, first of all, lambda is 0 is a very good solution, right? Because it's a trailing one here. It's a trailing thing here in the whole expression. So lambda 0 is a good solution. So then the next question which remains is b times c lambda squared, yeah, minus a minus c times b minus a times omega squared is 0. Well, that's actually a super simple equation. Then we get lambda is plus or minus the square root of what? Yeah, of this a minus c times b minus a divided by this bc. So those are the solutions. Well, remember, if lambda is positive, then we get this exponential growth. We get unstable. And if lambda is negative, then we get these stable solutions. But as you can see, when there is some finite number here, yeah, then we get a plus solution, but also a negative solution. So we get a stable and an unstable solution always. So you would say, oh, well, whatever happens, it will always be unstable, because yes, I have a minus, but I also have a plus root, and that is the unstable one. However, what happens if this is negative? If it's negative under the root, then we get imaginary. So how do I say, if this a minus c times b minus a is less than 0, which can be the case, then the lambdas are plus or minus I omega, and then the expression. And then we get oscillatory stable, because the solution then is just like it wiggles, and it will go on forever like this, and it will not grow and it will not decay. And if there's a little bit sun, wind, or damping, then it will decay, or slushing of fluids in the satellite, it will decay. So this is an interesting thing. So this when this is the case, then the thing is stable. Yeah. Or in other words, it's unstable, yeah, when this a minus c times b minus a is larger than 0. So that is an interesting conclusion. And when is that the case? So when is this larger than 0? It depends upon the magnitude, of course, of the a's. So if you say that the a is positive, and then also a minus c is a positive thing, and also b is larger than a, that is a case. Well, if you then put them all in order, then you get b larger than a larger than c. Yeah, and the other case is that, of course, the two terms are negative. Then you get a less than c, and then also b must be less than a, and then you get, of course, the intermediate. Then you have unstable motion. And that is a famous result. We call it the famous tennis racket or the remote control result. Because here, if we assume that we have a remote control, something like this, and then you have all these knobs on it, right? You can look for your channels here, and whatever, you can put it on and off, and then you can go to Netflix or Videoland, and you can change the colors or whatever. Anyway, this is your remote control. So remote control. Then, of course, due to symmetry, we see what the principal axes are, these three. Now, the smallest one, so this is probably where the I is the smallest. And that's this axis. And this axis is probably the axis where the I is the largest, right? So this must be the intermediate axis. Intermediate axis, where the I is in between the large and the small one. Meaning that if this is your remote control, then you can easily flip it like this, and then it will just finally rotate. I'm not going to do it here, I have no space, unfortunately. If you flip it like this, then it's also very stable. However, if you flip it like this, it will just tumble in the air. And you will think, oh, I can do it. Well, I can do it. I'm clumsy. Let me show you. I'm really clumsy, but I'll try. And whatever I do, the thing will never continue to rotate. So ideally you want this, right? And yeah, gravity, but whatever. And then it will go down and land again. But as you will see, that doesn't happen. What happens is, and it starts tumbling. Whatever. And of course I'm clumsy. You could say, oh, that's the professor, he cannot do it. Well, it's not the professor. I challenge you, you cannot do it either. So that is a famous result. You can also look at, for instance, a tennis racket. For those guys who do tennis, that's the same case. So if you have a tennis racket like this, here you have all the wires. Then again, what are the mass moments of inertia? Well, we know, of course, we have three axes again, three principal axes. Now my guess is again that this is where the I is the smallest. My guess is again that this is again the I, where the I is the largest. So this is the intermediate, right? So try and flip your tennis racket such and that it will only rotate about that. You will not. Impossible. Thank you for your attention. Sorry for the technical mishap. I have no clue what is going on. I tried to fix this ASAP. It took some time. I lost some customers, I see. How many customers did I lose? Yeah, 60 customers. Sorry for that. But the recording is okay, and you can still watch the recording and speed up and speed down. I'm going to stop with this, and then I'm going to open the Zoom meeting for the after lecture question and answers. Thank you for your attention.